little different with the midterm. I wanted to let you guys know. We said that we would release the solutions, but you probably have noticed if you looked at them, they're not up yet. It's because we decided to have you guys make midterm corrections if you want. So you can go through your midterm and you can resolve the problems that you got wrong. You can solve problems you didn't get to attempt. And you can submit them back to us, and we will give you some points back as a kind of, a bonus for resolving those problems. And the way it's going to work is that if you got over 40 on the midterm, then you get a maximum of 2 points back. If you got over 30 in the midterm, you get a maximum of 3 points back. And everyone else below that gets a maximum of 5 points back. So even if you get the whole midterm perfect, you're only going to get 5 points back if you, say if you scored below 30. But we really would encourage you to do that if you're, if you're even unsure about whether that's a good idea. It is a good idea because it's going to make you go through the midterm and, figure out the problems that you got wrong. Make sure you understand those problems, and then we'll release the solutions on the date of when the second homework is due. So when the last homework is due, the fifth homework is due, your midterm corrections will also be due, and we'll release the solutions then, and then you'll have a week between then and the actual little test. So you'll get to look through them that week if you hadn't worked on your midterm anyways. Okay, so we did this last year. I just forgot about it this year. One of my TAs reminded me. It worked out really well. I think people got a lot out of it. Are there any questions about that? Yeah, Jersey. I'm sorry. The same day that the homework is due. So 2 weeks from tomorrow. Okay, if there hasn't been a Piazza announcement about that, then I guess I'll just make one after class sometime, just so that we all are on the same page. Okay, today we're going to start the first of our advanced methods. Maybe at the end of the class today or at the break or sometime soon, I'll poll you as to what you want to hear next week, because we have a few options to what we could cover next week. There's, depending on interest, we may do one thing or another. So maybe I'll do a poll a little bit later. But the topics for this week are set. We're going to talk about ADMM and dual methods today. And we're going to talk about coordinate descent on Wednesday. Both of these are extremely popular methods. They received less attention in the optimization literature, probably classically, than the stuff we learned already. So that's why we're calling them advanced methods. They also are, in a way, more specialized. But they're, like I said, they're extremely popular in machine learning and statistics practice. So they're good things to know. So just to give you a recap of what we talked about last time, we did a case study of the generalized lasso problem framework. And we picked that framework just as a kind of working ground for showing off the different algorithms. In previous years, we'd done something different. There's nothing really special about the generalized lasso problem. It's just something that we could say a lot about in terms of, its dual, its primal, and all the different algorithms we could apply. So the logic you learned last week, you should think about as, being kind of broad enough that you can hopefully carry it forward to, whatever the problem that you're interested in solving for your research. We derived the dual problem, and we considered applying, like I said, all the algorithms we've learned so far to both the primal and the dual, and we saw basically that different algorithms had different strengths and were suitable for different situations. So if all you remember from the last week was just that last summary slide, then that's better than nothing. So take a look at the summary slide from the last lecture about the advantages of the dual, the complication that happens when you introduce regressors, all these things. So today we're going to talk about dual methods, and what naturally comes out of that is ADMM, the alternating direction method of multipliers. And I have to do a little review of conjugate functions in order to keep these fresh in our minds. So let's just do that now. So remember that when we talked about duality, we learned about what the convex conjugate of a function was. And if you give me any function f, I can define its convex conjugate as the maximum over all points x of that should, yeah, that's right, maximum of all points x of y transpose x minus f of x. So it's the biggest discrepancy between a linear function of x and the function itself evaluated at the point y. And this defines the conjugate function. So the reason we sometimes call it a convex conjugate is that the conjugate function is always convex. It's something that we saw, right? This is just a pointwise maximum of functions that are affine in y. So we saw them pop up a lot in dual problems because of this relationship, right? If I just take the negative on both sides above, I get that negative conjugate of f at y is equal to the minimum over all x of f of x minus y transpose x. And this looks like something that would appear in the Lagrangian, right, in the minimization of the Lagrangian. So this is our criterion function, say, if we had a constraint that involved x and y is the dual variable or the Lagrange multiplier we introduced, then this kind of constraint would pop up. This kind of form would pop up frequently. And in minimizing Lagrangian, we get out things that look like conjugates. So that's something that we talked about when we talked about duality. These last two relationships may not have seemed super critical at the time. You learned them, but you're going to see why they're so important today. If f is closed and convex, then the conjugate of the conjugate is the function itself. And the following holds, which is that x is a subgradient of the conjugate function at y, if and only if y is the subgradient of the original function at x. This one you saw, and I think you even proved on your homework. This is true, actually, if and only if x is a minimizer over all point z of f of z minus y transpose z. Okay, why is this last relationship true? Well, we can think about it in various ways, but let's just look at the we can think about it in various ways. Think about it from this perspective. If x is a subgradient of the conjugate function at y, then we can think about this is the conjugate function, and we know what the subgradient rules are for maxima, right? The subgradient for a maximum is the guy that achieves the maximum, right? That is a valid subgradient for a maximum of functions. So that's what all we're saying here. Achieving the maximum is also the same as achieving the minimum. It's the same thing as minimizing f of z minus y transpose z if we just take the minimum of what's inside here. So that's one way to see this. Another way to see this is to see that y being a subgradient of f at x, if we just look at this problem and we ask what values of x minimize this over all x, then we know also another way to figure that out is to take the subgradient of this with respect to x and set it equal to 0. What we'll get exactly is that y should be in the subgradient of f at x. So those are two different ways of seeing this relationship, either from the first statement or from the second statement, but they're both equivalent to this third. We just saw that directly. Okay? So any questions about that? This is, like I said, let's just spend a moment looking at this. This is actually extremely important for today's lecture. So we are in a subgradient of the conjugate function if and only if that point minimizes over all values, say z, f of z minus y transpose z. This relationship becomes a little more explicit and easier to remember when f is strictly convex. So what happens when f is strictly convex? Then you can see here, this function here as a function of z is strictly convex. Right? F of z minus y transpose z is going to be strictly convex if f is, because, as we've talked about before, if we have a sum of convex functions, only one of them needs to be strictly convex in order for the sum to be strictly convex. Right? That should be something that is natural to you just from the definition of strict convexity. And if this whole thing is strictly convex, then it has a unique minimizer. So actually, there's only one such point x that minimizes this. And remember, we were saying that x is an element of the subgradient of f star at y, the conjugate. And if there's only one point in the subgradient, it has to be the gradient. Right? So that's what this relationship is saying. If f is strictly convex, then well, we can see that that implies that the conjugate function is differentiable, and its gradient is equal to the unique minimizer of f of z minus y transpose z over all z. Okay? This also might have been on your homework. I think that was something at least related to this was on your homework. All right, so like I said, we're going to see this being useful today. So just remember this last equality. So we're going to talk about the dual subgradient methods, and gradient methods as a special case. Then we'll talk about their strengths, which is decomposability. So we'll talk about dual decomposition. We're going to see that there's a problem with the dual decomposition that is addressed by the method of augmented Lagrangians, but that sacrifices decomposability. And lastly, we're going to bring in ADMM, which is the augmented direction method of multipliers, which tries to get the best of both worlds. Has the strength of augmented Lagrangians, and it has the decomposability that we get with dual decomposition. Okay, so one way to motivate these dual subgradient methods is the following. What happens if we can't derive the dual in closed form, but we want to utilize the dual relationship? Right? We wanted to maximize the dual instead of minimize the primal. We don't know what the conjugate is in closed form. Okay, or we could just be interested in another perspective for first-order methods as well. So it turns out that we can actually still use dual-based subgradient or gradient methods with the relationship that I showed you on the slide 2 slides ago. So as an example, let's consider the problem minimizing some criterion function f subject to an equality constraint, ax equals b. Its dual problem is as follows. Maximize overall u, the negative conjugate of f star, evaluated at minus a transpose u minus b transpose u. So I'm not actually going to go through and derive this for you. By this point, I hope that going from here to here is not going to be challenging for you guys, since you've had lots of practice with deriving duals. Right? You know the steps. I introduce something like u transpose ax minus b, add that to this as the Lagrangian, minimize over x, it's going to give me this problem. Right? And we're going to use the property of the conjugate function's definition directly from that. So how could I apply something like dual subgradient or dual gradient, depending on whether or not this is differentiable, to this dual problem, if I don't know f star in closed form? Well, we can use the idea that we talked about 2 slides ago. First, let's just define the dual criterion as something like g of u minus b transpose u. Okay, so we have the dual problem minus f star a transpose u minus b transpose u. I'm just going to write this part as g of u. Okay, so what are the gradients of the subgradients of the criterion? I'm going to get, with respect to u, right, that's my dual variable. I have to know what subgradients of g is, and here this is differentiable, and its gradient is just minus b. Right, so the subgradients look like whatever the gradient is or the subgradient is of g of u, if this maybe isn't differentiable, minus b. So if I knew what these were, I could just use subgradient ascent on the dual, since it's a maximization problem, or I could think about doing subgradient descent if I just take the negative of this criterion, if that's what you're more comfortable with thinking about. So this is the question: how do we figure out subgradients of this function g? Well, let's just use the first property we know about the subgradients of a composition of a function with a linear transformation. So it's kind of like the chain rule, right, for subgradients, and that's that if I take a times subgradients of f star evaluated at minus a transpose u, then those are going to give me the subgradients of g, right? Because I take this linear transformation in here, and I transpose it, and I put out in front. That gives me minus a, and I had a minus sign in front, so that cancels the minus signs. Okay, so now we're really left with the problem of finding subgradients of f star. Right? The linear transformation didn't really bother us at all. But we don't know the conjugate function. Suppose we don't know it in closed form. Well, let's just go back to this idea, right, that we had a few slides ago, which is that a point x is in the subgradient of the conjugate evaluated at some point y. That point y here happens to be minus a transpose u. That's true if and only if x is a minimizer over all points, we said z, of f of z minus y transpose z. Again, this is y, so it ends up just being plus u transpose az. Okay, so what do the dual subgradient steps look like? First, we're going to have to solve this inner problem. We have to solve a minimization problem involving our primal problem. That's going to give us x. Once we multiply that by a, that gives us a subgradient of this function g. And if we subtract off b from that, that's going to give us a subgradient of the whole criterion. Once we have that, we can just perform dual subgradient ascent on the dual, where we go in the direction of the subgradient, not the negative subgradient because it's a maximization problem. Or like I said, if you don't want to think about ascent, you can just take the minus sign of this whole criterion and think about doing subgradient descent with respect to that, as we've learned before. Okay, so that's all this we're summarizing here. We just start with some initial point u naught, and then the updates look like this. First, we find xk to minimize. We can call it f of, let's say, z plus u at step. It's important we put step k minus 1 here, right? Because that was, if you think about where we're going to be evaluating this function, it's at the current iterate, which here would be uk minus 1 in the dual, times transpose a times z. And then we're just going to work backwards, right? If we multiply this by a, it's going to give us a subgradient of g. And if we subtract off b, that's going to give us a subgradient of the whole criterion function. And so to do subgradient ascent, we're going to move in the direction of that subgradient, right? So we just, like I said, multiply this by a to give us a subgradient of g, and then we have to subtract off b to give us a legitimate subgradient of this criterion function. Okay, so this would be our dual subgradient ascent algorithm. And this would be chosen in the standard way for subgradient method, right? We could take this to be diminishing, like 1 over k would be fine. Yeah. I'm sorry? Yes, thank you. Okay. So I think it's a neat perspective. What else is neat is actually the notation works out just fine. I claim that actually this is going to be our primal iterate at the end of the day. Right, we're solving the dual. Suppose we want to get a solution to the primal. I used x here for a reason. I claim that's going to be our primal iterate. Why is that the case? Just look at the form of this update. Say at convergence. What are we going to get? What is this that I've written down here? Up to a constant. What's that? Right, it's just the Lagrangian. Right, so at convergence, x, we'll call it x star. Let's say at convergence, x star is going to be a minimizer of the Lagrangian. At, say, whatever the limiting value of u is, right? Which is going to mean that x star is a primal solution. Right, assuming we have strong duality. So here we're assuming f is convex, and that's enough because we just have an equality constraint. All right, so we iterate this back and forth, and we're going to get, in the limit, we're going to get, if we're lucky, a primal solution and a dual solution. What about dual gradient ascent? It's really the same thing. The only thing that differs is whether we're taking a subgradient or a gradient here. And the only difference between those two is whether or not this is this value of xk that minimizes this quantity is unique or not. Because we saw that when f is strictly convex, there's a unique minimizer here. And therefore, this point x is actually the gradient of the conjugate function. And so we're actually doing dual gradient ascent. So the only difference between this set of equations and these ones down here is whether or not we have an element. So it is one of the minimizers. It is in the argmin, or it's equal to the argmin. The argmin, if there's just one minimizer. Okay, and if you wanted to do proximal gradient, like apply a prox operator or apply acceleration, everything carries through as you know. As you know already, for the primal problem, just apply to the dual, right? So there's really nothing that should be kind of confusing here. All this expression is doing is allowing us to evaluate the gradient of the subgradient. After you have that quantity, you already know how to do proximal gradient or acceleration. Okay, let's talk about its convergence just for a bit, because we can see something kind of interesting, and I think it's also going to be a nice refresher for what you learned for first-order methods. We're going to first recall a fact that was actually it was one of the midterm questions. So I don't think that this slide is going to give you that much more than what that was laid out in the midterm question. But if you wanted to get back some extra points, then you might study this slide. If f is strongly convex with a parameter, say d, then its gradient, the gradient of its conjugate function, is going to be Lipschitz with parameter 1 over d. That was one of the questions on the midterm. And look at what this is saying. If f is strongly convex, then it certainly is strictly convex, right? We know that's actually a stronger condition than strict convexity. So at least we know that the gradient exists. It's differentiable. But strong convexity implies even more. It actually implies that the gradient's Lipschitz. And you can see that its Lipschitz parameter is the inverse of what the strong convexity parameter is. So if it's very, if we have a very strong convexity parameter, then it's Lipschitz with a very small Lipschitz bound, and goes the other way as well. Okay, so here's just a proof sketch. You did this on the midterm, so some of these should look familiar, hopefully. Some of these steps. The first thing we do is we just say that the strong convexity, right, implies that we have not only a lower bound, we're lower bounded by a quadratic. That's what it implies, right? So it strengthens the lower bound we get from the usual notion of convexity, which is that it's always bigger than or equal to its tangent line. Now the function is actually always bigger than or equal to a quadratic, where the Hessian is actually d times I in that quadratic. The only thing that differs, that makes this statement differ from the one I said out loud, was that here we're actually considering x to be the minimizer. So the linear term is gone. There usually is a term that looks like the gradient of f of x transpose y minus x. That doesn't appear here because x is a minimizer. And so, if we're assuming f is differentiable, for example, then that term is gone because the gradient of f is 0 at x. So we have this bound for all y. And now we're just going to define 2 points. The first is going to be x sub u, which is the gradient of our conjugate at u, and x sub v, which is the gradient of f of our conjugate at v. And we're going to apply this fact just to the function either f of x minus u transpose x, or f of x minus v transpose x. Both of those functions are still strongly convex with the same parameter. Right? If f of x is strongly convex with parameter d, then, for example, for a fixed u, this is going to be true as well. And the same is true for a fixed v, right? You can just think about that. If f was differentiable, then, once I take two derivatives, this term is gone. So whatever held for f before still holds. So these two lines are just applying this fact to the first line is applying the fact to the function f of x minus u transpose x, and the second one is applying the fact to f of x minus v transpose x. And y here is being taken to be xv, and y here is being taken to be xu. So we get kind of symmetric inequalities from that fact. If we add these together, you can see that basically we're going to have these two terms and these two terms on both sides of the inequality, and same with these two terms and these two terms. No, sorry, these terms are different. But these two terms and these two terms will cancel. And if we just take that, what we get from adding these two together, and we use Cauchy-Schwarz and rearrange, we're going to get this fact. X sub u minus x sub v in 2 norm is less than or equal to 1 over d times the distance between u and v. But if we recall that x sub u and x sub v were just equal to the gradient, they're just placeholders, right, for the gradient of our conjugate function at u and our conjugate function at v, then we've actually just proved this fact. We've just proved that the gradient is Lipschitz with parameter 1 over d. Okay. So that's something that we know. And now let's think about what that implies if our primal function is strongly convex. So if f is strongly convex and it has strong convexity parameter d, then the dual gradient ascent, I claim, is going to converge at the rate 1 over epsilon, as long as we take step sizes. This should say less than or equal to 1 over d. That's a typo there. No, actually, no, d is right. Sorry. D is correct here. So why is this true? Well, if f is strongly convex with parameter d, then from the previous slide, that means that the conjugate of f is going to be Lipschitz with parameter 1 over d. Right? So that means that the gradient of the conjugate is going to be Lipschitz with parameter 1 over d. So if we're doing gradient ascent on a function f star, and I tell you that that function is Lipschitz with parameter 1 over d, then this implies that gradient descent with step size 1 over the Lipschitz constant, right, which in this case is just equal to d, converges at the normal rate that we learned, right, which is 1 over epsilon. Okay, so strong convexity in the primal implies that we get in the dual a convergence rate of 1 over epsilon. So some people look at this result, and actually the same thing has happened to me when I first saw this result. Look at this and say, wow, that's really unfavorable, right? Because look, we've assumed strong convexity, and all we get is the 1 over epsilon rate. Right? In the primal, if we assume strong convexity, then what we get is the log of 1 over epsilon rate. We saw that if you assume strong convexity, then you get a linear convergence rate. Here we've assumed strong convexity in the dual. All we get is the rate 1 over epsilon. So it seems to be like it's shedding some unfavorable light on the dual gradient method. But actually, we have to be a little bit careful here, because the rate that we learned for gradient descent assumed both strong convexity and that the function was Lipschitz. The gradient of the function was Lipschitz with a certain parameter. So if you look back at our slides on gradient descent, and you look back at how we proved that strong convexity rate, I think it's actually a homework question, you'll see we actually need to rely on both strong convexity and that the gradient of the function was Lipschitz. Both of those imply linear convergence rate. If all we assume is strong convexity, then all we get is the rate 1 over epsilon. That alone is not good enough, actually, for the linear rate. So what happens if we assume now that the primal function is both strongly convex and its gradient is Lipschitz? Then in the primal, it is true that it's going to converge at the rate log of 1 over epsilon. Right? So if f is strongly convex, and this is Lipschitz, then gradient descent, we know, on f gets the rate log of 1 over epsilon. Okay? And what happens if we assume both these conditions and actually now look at the dual gradient ascent method? We would hope that we get this rate too, right? If we just get 1 over epsilon, then it seems like going to the dual was a bad idea. Well, actually, the same thing is going to apply that gradient descent, or in this case, it's gradient ascent, right? If we're thinking about I should say on the dual, which involves the conjugate, still gets the rate. Log of 1 over epsilon. Okay, so the world is fair. There's nothing now that's out of place. So really, it's the same thing. We're going to do just as well in the dual. And the reason for that is that, well, right, 2 slides ago we said that, or this slide said that if f is strongly convex with parameter d, then its conjugate has a Lipschitz gradient. The converse is actually also true. So I'll leave that up to you to think about if you're interested in proving it. It's true that actually if a conjugate function has a Lipschitz gradient, that implies that the original function is strongly convex. Okay, so the converse is also true. Now let's apply that fact to f. So now if we have strong convexity and a Lipschitz gradient, then this thing is going to imply that the conjugate has a Lipschitz gradient, and this thing is going to imply that the conjugate is strongly convex. So actually, these two conditions imply the exact same thing about the conjugate function, and vice versa. So if we assume both of these together, then we're making kind of equivalent assumptions on the primal and the dual, and we get the same convergence rate. Okay, so I guess in rough terms, there's no kind of loss of efficiency in terms of the convergence analysis we get from doing the dual gradient method versus what we would have gotten to doing in the primal. Questions about that? Okay. So here's one of the main advantages of this dual formulation, and that's dual decomposition. And I'll give you a few examples where you can see why it helps so much. So a first example, we're going to think about minimizing a loss function or criterion that looks like the sum of fi of variable xi subject to an equality constraint on x, ax equals b. And let's think about this notation, right, x1 through xb. That actually denotes a block decomposition of our variable x into b blocks. Okay, so these could all be of different length. And they could be more than one variable. It's just a block decomposition of an n-dimensional variable into smaller blocks, b blocks. If we didn't have this equality constraint, then we'd be in a good situation, right? Because if we didn't have this equality constraint, we could actually just minimize each of these terms in the sum independently. We could actually do something in a parallel fashion. We'd send off to maybe b different processors the task of minimizing fi of xi, and then when they're all finished, we just would read off the solution from each of them. But when we have the equality constraint, that kind of complicates things, right? We can't actually do that because now the variables are being tied together in some way. They're being tied together because they have to meet this equality constraint. So that ruins our decomposability. The very powerful thing about the dual is that actually the dual decomposes in this case, even though the primal doesn't. And you can kind of guess why that happens. You can think about, remember our kind of high-level thought was about the dual is that it takes linear transformations in one spot and it moves them to the other. So taking the dual, in rough terms, should be moving this a into somehow the criterion function and out of the constraint. The constraint being the thing that was tying them all together. And let's see that in details. We can take this matrix A and we can partition it according to those blocks. So we're going to partition its columns according to the decomposition we have for x. So we're going to take this problem and we're going to write it as follows. Minimize over all x, fi of xi subject to the sum of ai xi equals b. All I've done is I've just decomposed the columns of A. And now let's think about applying the dual gradient or subgradient method depending on whether this function is strictly convex or not. And let's see what happens. So the first step, right, just recall, we're going to take x, and we're going to assign it to be, our new x is going to be a minimizer of overall z, of essentially the Lagrangian of this problem when we don't care about the terms that don't depend on x. So what's that? It's fi of xi plus u transpose the sum of ai xi. Right? So here actually evaluating at z, let's say. Okay. Remember, so z is of the same dimension as x, so it also decomposes into blocks. So z1 through zb. And let's look more carefully at this minimization. This is actually going to split up into separate minimizations across the blocks of z. Right? So instead of just doing that, I can think about for each I, I'm going to just look at the minimum over just ci of all the terms in here that involve zi. And if I'm lucky, they won't involve any other terms that involve any other zij's for j not equal to I. And I can do them all separately. And that ends up being the case, right? Because you can see here, this is just fi of zi. And this one still decomposes. It just ends up being plus u transpose ai of zi. There are no terms that involve zj when I look at all the terms that involve zi. So I can do this separately. That's the real key insight over I equals 1 through b. So that's the notion of dual decomposition. And now let's think about the algorithm. In the calculation of the subgradient of the dual criterion, so this step, I can actually separate that over all the different blocks. So each of these minimizations can be performed in parallel. Then once they're all done, I can just take the result of each one, and I can form the product ai xi, add that up back to get it into a product that looks like a times x, and subtract b. That's going to give me the proper subgradient of the dual criterion, and then I just take a dual update step. Okay, so sometimes these steps are referred to as broadcast and gather steps, and you can think about this picture here. Suppose I have some kind of central processor here, and at each step, say at step k, this is going to send out my current value of the dual variable to each of b subprocessors, or b units, capital B units. So this would be uk minus 1. Sends it out to each one, the same thing, because that's all they require. Each one then solves this minimization problem here. It can even store all the data that it needs for fi locally. Doesn't need to actually share that, right? Suppose fi depended on responses yi and other maybe predictor, other regressor variables, etc., other things. That's all just stored locally at each of these subprocessors. And each of these solves this minimization problem. AI is also only needs to be stored here, I guess technically. And then when it's done, it sends back its value of x, or it can actually send back the product ai xi, depending on what's more efficient, because that's all that's needed for the dual update step. Right? So each of these does that independently. They send back either xi or ai xi, whatever is more efficient, depending on the dimensions of a. And then this central node just does the dual update, which we call the gather step. Okay. So at one point, this was, I think, a very hot topic, and people were really kind of, they were kind of entranced by this notion that you get the separability in the dual, even though the primal, everything is tangled together. All right, here's an example with inequality constraints. Actually, it's not that much more sophisticated, and We can go on having more and more sophisticated examples, but I like this one because there's a nice interpretation of the steps, aside from the one I just showed you. So here I've just changed the equality constraint ax equals b to an inequality constraint. The sum of aixi is less than or equal to b. And really all that's different, right, is that I also like this example because we have to think about doing something else than just subgradient. We have to think about doing projected subgradient. So why is that? Look, I'm finding the subgradient in the exact same way as before. And my dual criterion function, it has the exact same form as before. So the calculation of the subgradient is just the same. There's no difference. Each unit individually just minimizes fi xi plus the current dual variable transpose ai xi. But the dual has a constraint now. Right? So because we have an inequality constraint here, when we introduce a dual variable, right, the constraint is that the dual variable has to be positive in each component because it's an inequality constraint. So there actually is a constraint in the dual. So taking a subgradient update in the dual may move us outside of the constraint set. So one thing we learned about the subgradient method, same thing's true with gradient method, is that if we can always project back onto the constraint set. Right? If we have a constraint set, it's easy to project. We just project back onto the constraint set. So these two steps are the same. The third step just projects back onto the constraint set in the dual by taking whatever we had from this update and just truncating at 0 if it ever goes below 0. That's projecting onto the set of variables that are positive in each component, the non-negative orthant. It's a very easy component-wise thresholding. Okay, so nothing is more sophisticated in terms of the steps. But there's a very nice interpretation of what's going on here. And I attribute it to Liev and Vandenberg, who is actually the co-author of that Boyd and Vandenberg textbook that we've been using. I mean, I'm not sure that actually he came up with this. I found it in things that he has written, so it could be elsewhere as well. So let's think about it as follows. We have B units in a system. That's each of the components of X, each of these blocks. And each unit has its own decision variable. And that's how to allocate, say, some goods. Okay, I don't know, maybe it represents money or something. It doesn't really matter what we think about. But this is how much we're allocating of the good of that unit. That's what xi stands for. And the constraints here are constraints on shared resources. So each row of A, tells us that if we take some combination of the allocation we have for the allocations we made for the first set of goods, and we take other combinations of the allocations for other goods, then we can't exceed some limit, B. It's a limit on maybe how many resources are available. This is a very natural thing if we think about we have different systems that are trying to coordinate. In this case, we can think about each dual variable as the price of the resource that's referred to by that row. So we have one dual variable for every row of A, and we're going to call that uj. And we can think about it actually as the price of whatever the resource that row is referring to. The dual update, let's look back at what it looks like. It really just takes where we were, and it takes the leftover amount, essentially, from what we spent with that, what we allocated in that resource, and what its limit was. And then it soft thresholds that, so it truncates it at 0. So that looks like this. The dual variable at the current step is what we had at the previous step, minus some step size times Sj. And Sj is just, I have it written down there, but you can think about it, it's just the limit that we have for the jth resource, and it's the difference between that and what we actually ended up spending. Okay? Or I can think about it's the jth row of A transpose xi, transpose x. And we call these the slacks. So let's look at how much is left over. And then we're going to truncate that to be positive, right? Because it has to be a price. So we're not going to let the prices go negative. So this step we can think about, if Sj is negative, right, then the resource is overutilized because we've actually spent too much, right? This is negative, then we've allocated too much compared to how much we're allowed to be allocating for that resource. So we're going to drive the price up, right? If I take what it was before and I subtract out something negative, the result is just something that's larger. So if the resource is overutilized, we're going to make it more expensive. If the resource is underutilized, so this is positive, we're going to decrease the price, allow ourselves to kind of expend more of that resource. And we're not going to let the price go negative, right? Because if this is positive, then it could be the case that this difference goes to 0, but we're just truncated at 0. So it's a nice interpretation of the dual subgradient method with inequality constraints, called price coordination. Okay, let me tell you what the problem is about the dual subgradient method, and then we'll take a break and we'll come back to a fix for it. So one disadvantage of these dual methods is that we require strong conditions to ensure that the primal iterates actually converge to solutions. So I thought about giving details here, but I don't think it's really worth it. I think it's just helpful enough for you to know that we're iterating, right, between the essentially primal and dual iterates, but all we've really proved when we look back at our results is that the resulting iterates, they converge to the criterion values. That's what we proved with most of the first-order methods. And we've really proved the same thing with a lot of the other methods as well, that we get a convergence of criterion values. If we actually want the individual iterates to converge to solutions, it requires more conditions typically. And they usually aren't too much more stringent. However, just because of the nature that we're actually using the dual, we're not going to get primal convergence here without pretty strong conditions. So we do get dual convergence. We can get that these U's converge to solutions under a little bit more conditions, but for reasons that maybe I didn't really want to go into, the primal iterates can actually even be infeasible in the limit. We can actually even get, under a set of conditions, that we get a convergence of criterion value. So this converges to the optimal criterion value. The dual iterates converge to solutions, but not only are the primal iterates not solutions, they're not even feasible in the limit. They could actually not even satisfy AX equals B. Okay, and maybe one way to think about that not being too surprising is that we're not projecting onto a constraint set. There actually is maybe some residual slack, right, at every step for the equality constraint AX equals B. We're hoping that's going to drive ourselves to that feasible region, but it just requires stronger conditions. One fix for that is something that we call the method of augmented Lagrangians. All we do is we add a term to kind of smooth out the primal criterion function that has no effect on the solution. Right? It doesn't change the solution if we add some constant rho over 2 times the norm difference between AX and B if AX equals B as a constraint. So this doesn't change the solution of the problem, but it actually helps us with that convergence issue. Under much weaker conditions, we get convergence in this case to primal solutions. So let's take a break, and we'll come back and talk about that. The augmented Lagrangian. So you can see where the name comes from, right? As we discussed before, this is really minimizing the Lagrangian for this problem. The only difference, let's ignore this term for now. The only difference is that I don't have a term that looks like maybe minus U transpose B, which I would have needed if I'm actually writing out the Lagrangian. But in minimizing that over X, it doesn't have any effect. So I can think about, without this term, the dual subgradient or gradient steps as choose X to minimize the Lagrangian, and then update U, essentially according to the difference in how I'm not meeting the constraint. And what is happening here is that we're augmenting the Lagrangian. We're sticking a term in this step that looks like rho over 2 the norm squared distance between AX minus B. And another way of thinking about that is that we're adding a term to the criterion function that's just exactly that same thing, rho over 2 the square distance between AX and B. This doesn't change the problem, like we said. There's no difference between the solution to this problem and the one we had before, so we haven't hurt ourselves in any way. it just ends up helping with the convergence issue that I talked about before. You can think about it, it's really kind of introducing some kind of curvature into the lost function, but it doesn't really matter because it doesn't change the solution. So when A is full column rank, if we think about this matrix having full column rank, then this is guaranteed to be strongly convex. And so it really is true no matter what F is, right? Because if A is full column rank, then if I take two derivatives here, then the Hessian is just something like, I think it's just rho times A transpose A. And if that has a lowest eigenvalue that's bounded away from 0, that's not 0, then this term is strongly convex, so is this combination. And so really there's actually a unique minimizer here, and that's why we can write an equal sign here. In general, if A is not strongly convex, then there could be more than one minimizer here. So I should have written, to be super precise, an element sign there. But the method still works, right? It would just be then the subgradient steps rather than the gradient steps. So there's no problem with A being column rank deficient. There's one other difference here between these steps and the steps you saw before. So there's this extra term. The other difference is this. Look, we're actually not even choosing a step size via usual rules. We're choosing the step size to be rho. So we're letting whatever we put here dictate the choice of step size here. We're matching them. And there's a motivation for that. And that comes from trying to preserve the stationarity condition for the original problem, after we've added this augmented term. And that's what we're showing here. Xk minimizes this over all x. That's what the first step says. Right? So that means that 0 should be a subgradient of this function. And we can split it up like a subgradient of f plus A transpose u plus this thing, which is differentiable, and its gradient is just A transpose rho times AX minus B. Okay, and if we happen to choose if we happen to choose this to be equal to rho to be equal to the step size, as we did back here, right? Then this whole term here is just equal to UK, right? Generically, UK might be different because it might have a different choice of step size. But under the choice of step size, TK equals rho, then this whole term here is just UK. So it looks like 0 is a subgradient of F plus A transpose U. And this is the stationarity condition for our original primal problem. So it's just a helpful matching in order to preserve that stationarity condition. That's all that this choice is doing. Under milder conditions, then what is needed for dual decomposition? And again, I'm withholding the details here because I think it's probably not worth our time to go through them. But if you're interested, then I put a reference at the end that you can read about the distinction in convergence properties. You can show that the primal iterates approach feasibility, at least in the limit, and the KKT conditions are satisfied with x and u, and they approach optimality. Okay, so we get actually convergence of the iterates themselves under milder conditions than we would get if we just used dual decomposition, which has rho equals 0 here. So that's the advantage, much better convergence properties. And the disadvantage is that we lose decomposability. So if we go back, if this decomposed, right, if x decomposed, then this term is really hurting us in the sense that it's tying all the problems back together. So by augmenting Lagrangian, we've helped ourselves out with convergence properties because we've kind of smoothed, in some sense, the original criterion function, but we've just killed our ability to separate this across chunks and variables. So I'm actually not super familiar with the history of the dimensional Lagrangian. Maybe Javier can tell us. Did people pretty soon after this go towards alternating methods, or was it a? I don't know the history, yeah. So I wasn't sure whether people struggled with this issue for long. I know that ADMM is quite old. It gained popularity a few years ago in machine learning statistics, but the idea is itself quite old. So at least the fix for this issue is quite old. And that is what we call the alternating direction method of multipliers. And it goes by other names as well, like the alternating Lagrangian method, I think I've seen it called. You may hear it called slightly different things than this, but ADMM is certainly the most common. And it tries to take the good convergence properties of augmented Lagrangians and preserve the decomposability we get with the kind of plain old dual decomposition method. The short answer is that all we do is that we force decomposability, even if doesn't happen. So we actually just minimize this over each block individually as if we had that decomposability. And in a little more detail, we can think about it for a splitting of two variables. Let's suppose we had this minimization problem, f1 of x1 plus f2 of x2, and we have this constraint, right, ax equals b. It's written out like this. So we're going to do the same thing as before. We're going to augment the objective, just like the method of augmented Lagrangians. And all we're going to do is that we're going to take this augmented Lagrangian, and we're going to first minimize it over x1. And then we're going to take that value, and we're going to plug it in. And then we're going to minimize that over x2. Even though this doesn't necessarily decompose into two separate minimizations over x1 and x2, we're just going to treat it that way. Okay, there's a slight difference here between treating it as two separate minimizations in an ad hoc fashion and doing it in this fashion. And this is something people often skip. It also relates to something that people often skip with coordinate descent. And that's that it actually matters that after we minimize with respect to x1, that we take the new value of x1 and we use that to minimize the Lagrangian. Okay, so that, at least as I've explained it, it seems like it may hurt decomposability because we can't actually do it in parallel. At least we can solve smaller subproblems. Okay, so at least we can split this up into smaller subproblems that we can solve perhaps more efficiently than the full problem. But we don't have, at least as I've written it, the full decomposable power of the dual method. Now, if you're interested in reading about approximations to this where we actually do these in parallel, say, and we forget about the fact that we're supposed to be using x1k here, then again, you can read about that in the reference I gave you at the end. There's been some recent work on trying to really parallelize ADMM. Okay, so in summary, we repeat the following steps: minimize the Lagrangian over x1, take that value, plug it in, minimize the Lagrangian over x2, take both those new values, and make a dual update, just by looking at the residual from the constraint. And just for comparison, right, the usual augmented Lagrangian, which is sometimes called the method of multipliers as well, it would just replace these first two steps with a joint minimization over x1 and x2. Okay? Any questions about ADMM before we go to examples? No? Okay. We're going to talk about convergence guarantees just for a bit first. And again, there's more information in this reference at the end. So this is what we get under modest assumptions on f1 and f2. I think all they have to be is convex and closed. Maybe there's no conditions on differentiability for sure. And a1 and a2 don't need to be full column rank. That's not important. For any fixed value of rho, we get that the primal iterates approach feasibility. So we get residual convergence. We get objective convergence. This shouldn't be surprising because that comes out of all of our analyses for these first order methods. And we get the convergence of dual iterates to a solution. We don't generically get the convergence of primal iterates to a solution, but under a few more assumptions we do. And they're certainly much less strict than the assumptions we get for the dual decomposition method. Okay, so it has maybe not slightly as strong convergence properties as the augmented Lagrangian method, but very close. And as written, doesn't quite decompose as well as the dual decomposition method, but again, it's close. So it's kind of a combination of both of these ideas. It tries to balance those two strengths. A very interesting question is about its convergence rate. It's moving very quickly, so I could actually be out of date with the state of the art at this point, but as far as I can tell from when I looked last, which was not too long ago, it's still not known in general. There are certainly special cases that people have studied in detail, special problem cases, but there's nothing like, if f is convex and Lipschitz gradient, this kind of generality, then we get this convergence rate. The consensus seems to be, both in terms of theory and in examples, that it behaves like a first-order method. So it has kind of the same convergence properties in the sense that you would need to iterate a lot for a very accurate solution, but it gives you a pretty rough solution in a few iterations. So it's certainly more like a first-order method than a second-order method. Yeah.
So by solving for x1, then solving for x2, we're not solving the same problem as before. We get a different solution if we were to minimize both at the same time. Is that correct?
At this step, yes. At the kth step, you would. But in the limit, you wouldn't under some of these conditions. Yeah. It's a good question. And actually, also, you'd have a different algorithm depending on how you set it up if you solve for x2 first and then x1. So we're going to see towards the end, when I give some examples pretty soon, that like deriving duals, setting up an ADMM algorithm is, there's not one way to do it. You can do it in different ways, and you end up with different algorithms. So there's kind of an art to it in a sense. Any other questions? Yeah.
If we care about strict feasibility of our solution, should we not use this?
Strict feasibility?
So apparently the residual just converges to zero, right?
Uh-huh.
So at any step there might be an actual difference.
Oh, yeah, I see what you're saying. You mean if I want it to be feasible when I terminate the algorithm?
Yeah.
Yeah, it's a good question. Typically, the setup that we use, you'll see that the equality constraints we introduce are really just for convenience, like they were in the dual. They don't have meaning. If we had equality constraints that we really cared about, then I might actually wrap those into one of these Lagrangians and perform like a projection here or something like that. I'd write it as an indicator and maybe not keep it as an equality constraint. But it's a good question. I mean, unfortunately, the examples I'm about to give you, they all have equality constraints for basically because it helps us drive the algorithm. Otherwise, you'd have to do something in these steps to project onto that equality constraint or something to preserve that at a finite number of steps. Yeah?
You have some constraints on saying the x has to be inside some cone or PSD.
Uh-huh.
When you're doing this argument step,
I'm sorry? Say it a little louder.
say the x has to be in some positive semi-definite cone.
Uh-huh.
Like telling these methods, you have to do the projection again.
Right. Yeah, it depends on how you've set it up again. But you're right. If I have a constraint, then I would write that as an indicator. And so I would think about, suppose I have a constraint on x1. Then I'd wrap that as an indicator into this function. So I think about f1 has something smooth plus an indicator for the constraint. And so here, I'd have to do something that minimizes the Lagrangian over that constraint set. If you've decomposed things in a helpful way, it could be that constraint is very easy to deal with. Right? So you can, as we'll see with examples, you can introduce equality constraints in any way that's helpful. So if you did it in a way that was helpful enough that one of these steps had a proper constraint on x that was like, you could set a PSD cone or something, then it may just be, if you're lucky, a simple kind of update. I guess with a PSD cone, probably the best thing we could hope for would be projection onto it is still an eigendecomposition, so that would be expensive.
But does it class have the minimizer effect? It's actually the separating dual error.
Yeah, that's still true. There's nothing, we didn't violate anything. That's still true. Yeah.
I was wondering, relative fixed form.
That's a great question. I think talk about it in 2 slides, but here it's fixed. We're considering it fixed here.
How do you choose the fixed?
I'm sorry, how do you choose it?
Yeah.
2 slides. We'll talk about it in 2 slides. No problem. It's a good question. So let me introduce just a slightly different form for ADMM. I haven't done anything else here that's that's meaningful, except for I've just, instead of writing the dual variable as u, I've written it as w, which is u over rho. Just scaled the dual variable. It ends up being helpful in remembering the ADMM steps. I find at least I remember them easier like this than before. First of all, the dual update, there's no rho here. So you just take w, which is your new parameterization for the dual variable, and to update it, you just add to what you had before the residual from the equality constraint. And the minimization steps you can check just from some pretty simple calculus. They reduce to the following. Instead of having a term that looks like, the norm of the constraint violation squared times rho over 2 plus, u transpose something, you can wrap it all into one term. And it looks like the constraint difference plus the dual variable. So that's how I tend to remember it. You take the original function, and you add rho over 2 times the norm of the constraint violation plus the dual variable. And that gives you all the steps. To show this is equivalent to what we saw before, just expand this, and then throw out terms that don't depend on x1 and x2, and you'll see they're the same steps. That's all it is. So here we get to a few practicalities. And I want to save some time for examples, but we're running a little short on time, so I'll try to go through this quickly. Practically, you're going to need to run a lot of iterations for ADMM to get a very accurate solution. So that's more evidence that it's like first-order method. This is kind of more an empirical consensus rather than a theoretical convergence rate. Choice of rho can definitely greatly influence practical convergence of ADMM. So this is a good question that's asked earlier. Here is one strategy that people take in practice for how to choose rho. And that's, actually, let me first give you the two different ends of the spectrum. If rho is too large, then there's not enough emphasis on minimizing the primal, right? If we make rho really large, go back to the problem, then this term is kind of dominating minimization of these two functions, f1 plus f2. And so maybe we don't get convergence of primal solutions as fast as we'd like. If rho is too small, then we don't have enough emphasis on feasibility, right? Because this term is multiplying ax minus b. Maybe there's not enough weight on that. And so we don't get the primal iterates approach feasibility fast enough. And so there's a strategy that it's kind of more of a heuristic that's given in this paper by Steve Boyd, with a reference at the end, that people use in practice, I think fairly often, but it doesn't come with convergence guarantees. So the convergence guarantee is that if rho is fixed, it converges to the solution no matter what rho is. So that's pretty nice. Even if you had a kind of poor choice of rho, it'll eventually converge. You may be a little slower, but it'll eventually converge. Now, when people start trying to optimize ADMM for efficiency, they vary rho. So they do something where, I'll explain the heuristic in words. You look at the primal residual and the dual residual. If the primal residual is too big, you make rho smaller, because then we're going to put more emphasis on minimizing f1, f2. If the dual residual is too big, then you make rho larger. And that actually ends up emphasizing feasibility more, if you think about the relationship in the primal and the dual. And so you might double or half rho depending on whether the primal or the dual residual is larger at each iteration. Now, that's not going to converge guaranteed to the solution. So it's kind of a funny situation where I think this is something people use more often in practice, but we don't really know that it converges. One thing you can do just to be super careful is that you could do this strategy, say, for 5,000 iterations, and at 5,000 iterations, you could just stop and keep rho fixed. And that could be your rule. And if you do that, then rho is going to be fixed eventually, so it will converge eventually. And maybe you hope that by 5,000 iterations, you've gotten some good leverage out of using this strategy like this. So there's a bit of trickery that goes into deriving or transforming problems that fit into ADMM form, and it's like deriving duals. You can do it in different ways. I had 3 examples to show, but I wanted to show the last one because we don't have that much time left. Go ahead and look at the first 2 if you're interested. Another way of doing alternating projections, and another way of solving generalized lasso problems, because we spent some time on that last week. I want to talk about sum of norms regularization as our example before we head out for today. So the problem we're thinking about solving is a problem where we've decomposed our primal variable into different blocks, and we're going to call that each index block's I sub g, for g going from 1 through capital G, and we're placing an L2 norm on that block of variable. And we could be doing something else in regression. I just put down regression here because it was kind of the most transparent. So this, when I use the 2 norm here, this is usually called the group lasso problem. In previous years, we spent time talking about the group lasso problem because it's an interesting problem from the perspective of optimization. It's a lot harder than the lasso. This year, we spent more time on the generalized lasso problem just for no reason, just to change it up, which is also harder than the lasso. So it's an interesting problem from the perspective of how to optimize this criterion, or if this was a logistic loss or something as well. If we change the 2 norm to another type of norm, then this is known as sum of norms regularization. So we could think about this being more general, just a kind of a different choice of norm, even potentially different for each group of variables. If we use the 2 norm, then this encourages sparsity in groups of variables. That's why it's called the group lasso. So we would be doing a regression problem here where we're trying to set groups of variables to 0 rather than individual variables to 0. You can read more about the group lasso, or even just take its KKT conditions and look at them if you want to find out more about why that's true. So how do we apply ADMM to this? There are no constraints, right? So like we had when we were talking about dual problems, we look at this and we don't see an easy way to apply ADMM. Well, now we do something very similar that we do with dual problems. That we introduce auxiliary variables so that we can have constraints, and then it allows us to apply ADMM. That's typically how we apply ADMM. So in this case, we're going to set alpha equal to beta. And we're just going to change all appearances of beta in this term with alpha. So it's the same loss, but I've changed these to alpha, and I've just introduced the constraint that beta is equal to alpha. Okay, so I have a set of variables alpha and beta, and alpha is my auxiliary variable. Now I look at this problem, and I think about applying ADMM to this. So this is F1, this is F2, and then I have beta minus alpha equals 0 for my equality constraint. So beta is one block of variables, and alpha is the other. The ADMM updates are actually really quite easy here, and they're computationally not bad at all, and let's go through them. So for beta, the beta update, I want to take this loss, look at all the terms that involve beta, and that's really just the first one. I'm going to throw away the second one because it doesn't involve beta. And I'm going to add to it rho over 2 times the discrepancy in the constraint plus the dual variable. So I'm adding to it rho over 2 times the norm of the discrepancy in the constraint, so that'd be beta minus alpha, and plus the dual variable, w. And I want to minimize this over beta. Well, because of the way we've arranged it, this is a very easy problem, right? This reduces to a ridge regression. It's like solving a regression problem in closed form. It was hard before because of this kind of complicated penalty here, right? But now, since we've introduced alpha for this term, this particular Lagrangian minimization over beta is very easy. So we can just write that as x transpose x. If you want to figure out where this came from, take the gradient of this and set it equal to 0, or just rewrite it like a ridge regression problem, either one, plus rho I inverse x transpose y plus w transpose, plus rho, I believe. Yeah, rho times alpha minus w. Okay, so beta step is done. That's what we need to do for the beta step. How about the alpha step? Got to take the argmin over all alpha of our criterion, which is up in the slides, that involves alpha plus the same term. So it just looks like the sum of alpha ig in 2 norm plus rho over 2 beta minus alpha plus w. So this is a very easy thing to optimize because this decomposes into separate minimizations over each group. I can do each group separately, right? Because I can write this also as sum over groups, of norms over groups. And so for each group, I have to just minimize something like least squares lost to alpha with no regressors. There's no matrix. It's just going to be alpha ig minus something plus this. And that's a very easy problem. It actually is just the prox operator of this norm. And we learned what the prox operator of the L1 norm is. The prox operator of the L2 norm is very similar, and I wrote it as R in the slides instead of S for soft thresholding. And it's really just shrinkage, and I'll write down what this is in a second, of beta plus W. And R of, let's say, R at the level t of some vector x is just 1 minus t over the norm of x times x. So this is a type of L2 shrinkage. And actually, we take the positive part here. We don't let it go through 0. So how did I figure this out? You could have done the same thing by just thinking about how to optimize this for just a single group of variables ig, and you could have taken, say, the subgradient of the L2 norm and then the gradient of this part and figured out that this was the solution. So it's an L2 shrinkage. It might remind the statisticians of Stein shrinkage. And the very last thing we do, right, is we just take a dual update, which is W plus the violation that we have right now, beta minus alpha. So that's our algorithm for solving the group Lasso problem. It's not sophisticated. Each step is very simple. It's fairly efficient. It doesn't converge to high accuracy quickly, but we can, if we want a rough solution, it's certainly a good candidate. One thing to say is that actually a very similar logic would carry through even if the groups are overlapping. So here we assume that the groups were disjoint, so that I actually could do each of these minimization problems separately, and each one reduced to this. If the groups were overlapping, then we can actually just parameterize the problem a little differently. So we, instead of introducing an alpha for the whole vector beta, there's kind of a little more clever thing we can do. And then we can solve the overlapping group lasso problem here with ADMM. Overlapping group lasso is an extremely hard problem to optimize outside of ADMM. So it just goes to show you the simplicity of the ADMM framework. Okay, we're out of time. I'd like just to maybe close by saying that you can think about ADMM as a very simple way to get an algorithm for a problem that may be complicated. So it's good for cases in which you've kind of exhausted other faster options, and you want something that you can kind of do with simple update steps, which you typically can do if you parameterize it properly. All right, next time we'll talk about coordinate descent. See you then.